So we can make a logic device using MOSFETs, and we can make especially nice ones when we combine N-channel MOSFETs, NMOS, and P-channel MOSFETs, PMOS, made with identical but opposite characteristics, and we call that CMOS for complementary MOSFETs. So both the NMOS and CMOS transistors are made on the same substrate, and so they have a nice, very symmetric response functions. And so let's consider the action of this CMOS NOT gate. And notice it has two enhancement mode MOSFET transistors. And remember, enhancement mode MOSFETs are off at 0 voltage from the source to the gate. And so they have to be turned on. And we use that in this case. And so both these MOSFETs have the same threshold voltage, which is A. So for the NMOS kind, that means that the gate has to be A volts above ground, above the source. And for the PMOS, which we have on the top here, the gate has to be A volts below the source, or in other words, minus A. And so to make this work, we have to have the drain voltage greater than A. And we connect everything to ground. So notice if they're both on, there's a clear path for current to flow from ground to from the drain voltage source to ground, though I think it'll never happen that way. So imagine Vin. So first of all, if Vin is 0, then the voltage drop from the gate to the source on the NMOS part, M1, is 0, so it is off. On the other hand, we have a minus 5 volt drop from the gate to the source on the PMOS kind, which means it's on. So if this is on, it means there's a path here that's connected, but no current flows. So we must be in the case where V out equals VD. This is off, so it's basically like we put this switch on, we have a switch there, and we turn it on. We have a switch here, we turn it off, so V out is connected to VD, and it's high. If we switch V in to VDD, then everything switches around. Now this voltage difference is 0, this voltage difference is plus 5, this one turns on, this one turns off, and V out is connected to ground. And that's the situation we just talked about, these two situations, this one here and this one here. Now notice we can raise V in from 0 without this changing until we get to the threshold voltage, which in this picture I've drawn at 1.25. And so nothing changes then, basically because we're far away from this one turning off and this one hasn't turned on yet. Likewise, we can come down from 5 volts here for a ways before this one starts to turn on, and so we have that will lead to a nice large noise threshold. Vn doesn't have to be 0, it can be anything up to whatever this threshold voltage is A, and we can be sure that the output will be either high or low. Now, it's interesting if VDD is greater than twice the threshold voltage, in other words, greater than 2A, we can get in the situation where both of these will be on, and so in that case we can imagine that if we're halfway in between, then this one is on because we're greater than A above 0, and this one is on because we're more than A below VDD, and that's why we have to be greater than 2A. In that case, they're both on, and V out should sit right in the middle if they have the same resistance in both of them. So if they're both active region, then it'll be in the middle. If they're not in the active region, well, it should still sit in the middle because they should both be the same voltage between the drain and between the source and the gate. So what one gets is this nice symmetric form for the output voltage versus the input voltage. And you can calculate these curves exactly using the formulas for the response of an enhancement MOSFET that we learned last time. One can also then use these to make NAND and NOR gates by putting these NMOS and CMOS transistors either in parallel or in series. So in this case, we can look at this one. I believe this is the NAND gate. If both V1 and V2 are high, meaning at VDD, then this transistor will be on, connecting this to ground. This one will be connected to ground, so this will also be on because there'll be a large threshold there, opening this up and pulling V out to ground. Meanwhile, with V1 and V2 both at high, both of these transistors are off, so there's no connection this way or that way, and V out goes to ground. So both of them on, both high, means this is low. But if either one of these is low, then one of these will be disconnected, and one of these will be on, and we'll have a connection here, and this will go high. Likewise, if they're both off at 0, then both of these will be on, pulling this up to VDD. If we just change these around, we get the NOR gate, which I invite you to go through the logic of yourself.